In this section, we will look at the structure of an atom from the perspective of why it is important in the world of basic electricity. The structure of the atom determines the type of conducting properties a material may exhibit and how a particular atom will interact electrically with other dissimilar atoms. It is from these properties that we obtain semiconductor components, resistors, capacitors, inductors, batteries, and power sources. Let's take a look at the structure of an atom. An atom is made up of a nucleus and one or more electrons. The nucleus contains most of the mass in an atom and is comprised of neutrons and protons. The protons are positively charged particles and give the nucleus a positive charge. The neutrons contain mass but exhibit no charge imbalance. The electrons or electron contain very little mass and have a negative charge. The law of electrostatics states that like charges repel and unlike charges attract. So there is a very strong attractive force between an atomic nucleus and its electrons. This strong attractive force in the atom is balanced by the centripetal forces due to the speed of the electrons as they travel in orbits around the nucleus. The orbital relationships in an atom may be considered to be somewhat analogous to the Earth and man-made satellites, except the attractive forces that bind a satellite to the Earth would be gravitational instead of electrostatic. Satellites are maintained in stable orbits because the centripetal forces due to their orbital speeds exactly balance the gravitational attractive forces between Earth and satellites. It takes so much energy to place a satellite in an orbit. The higher the orbit, the more energy it takes to lift and put it there. Electrons are similar in that they orbit in shells or energy levels. The higher the energy level, the higher the shell. Atoms absorb and give off energy in a variety of ways. When an atom absorbs heat energy, its electrons move to higher energy levels, and the atom actually physically expands to occupy more space. This phenomenon can be observed in the thermal coefficient expansion of materials. Atoms also absorb electromagnetic energy, and some release this energy in specific wavelengths of light that can actually be used to tell exactly what atoms are present in a material. Now that we have introduced the atom and the concept of energy levels and shells, we will discuss this in more detail later. Another feature of an atom is its magnetic properties as represented by the electron theory of magnetism. As electrons orbit an atom, they are also spinning on their axis, much as the Earth rotates each day or spins on its axis as it traverses its orbit around the Sun. If the electron spin is random from one electron to another, we say that the atom does not exhibit any magnetic properties, since the magnetic effect is canceled. However, if most electrons are spinning in the same direction, the atom will exhibit magnetic properties, and the more electrons there are that are spinning in the same direction, then the stronger the magnetic properties. Protons in atomic nuclei also exhibit magnetic spin properties that are used as the basis for the magnetic resonance imaging device, the MRI. The electron configuration is the orbital description of the locations of the electrons in an unexcited atom. Electrons orbit in shells or energy levels. The higher the orbit, the higher the energy level. Atoms react with each other based on their electron configurations. The outermost electron shell is the most important as far as conductivity properties are concerned. The configuration of electrons in the outermost shell determines if the atom is a conductor, insulator, or a semiconductor. This model of an atom was developed and presented by Niels Bohr in 1913. In atomic physics, the Bohr model depicts the atom as a small, positively charged nucleus surrounded by electrons that travel in circular orbits around the nucleus, similar in structure to the solar system, but with electrostatic forces providing attraction rather than gravity. Electrons and protons have the same amount or magnitude of charge. The charges are of opposite polarity, negative for electrons and positive for protons. The protons give the nucleus its positive charge. In the aluminum atom presented here, 13 negatively charged electrons are represented as being in shells or energy levels in orbit around the nucleus. Each shell for a particular atom has a number of electrons in it. The nucleus contains 13 positively charged protons and 14 neutrons, which have no charge. As stated in a previous slide, most of the mass of an atom is in its nucleus. For example, the mass of the hydrogen atom has 99.5% of its mass in the nucleus. This atom has an equal number of electrons and protons and is said to be electrically neutral. If an atom has more electrons than protons, it is said to be negatively charged or to be a negative ion. If an atom has more protons than electrons, the atom is said to be positively charged or to be a positive ion. The process by which atoms gain or lose electrons is called ionization. This slide depicts the copper atom. A nucleus containing 29 positively charged protons is surrounded by 29 electrons orbiting the nucleus in a number of different shells or energy levels. In this example, each energy level or shell is labeled. There's the K, L, M, and N shells, all containing different numbers of electrons. The K shell contains 2 electrons and is said to be complete, since this is all the electrons that can orbit a copper atom in this energy level. The L shell contains 8 electrons and is complete also. The M shell is complete with 18 electrons, but the N shell only has 1 electron when it could hold more. It is said to be incomplete. Bound electrons are electrons in the inner shells of the atom that are bound to the atom because of the strong attraction of the oppositely charged nucleus. In this copper atom, shells K, L, and M contain bound electrons. The outermost shell of the atom is called the valence shell, and its electrons are called valence electrons. In this example of the copper atom, the N shell is the valence shell. Because of their greater distance from the nucleus and because of the partial blocking of the electric field by bound electrons in the inner shells, the attracting force exerted on valence electrons is less. Therefore, valence electrons can be set free easily. Whenever a valence electron is removed from its orbit, it becomes known as a free electron. Electricity is commonly defined as a movement of these free electrons through a conductor. Electrons can flow in all matter, but electrons flow more easily in some matter than in others. A good conductor is a material through which electrons can flow easily with little energy applied. They offer very little resistance to the flow of electrons. The electrical conducting properties of various materials are determined by the number of electrons in the outer valence shells of their atoms. The outer valence shell never contains more than 8 electrons. Generally, a conductor has an incomplete valence shell of 1, 2, or 3 electrons. The valence electrons in a conductor are held loosely. There is room for more, and a low voltage will cause a flow of free electrons. Metals such as silver, copper, gold, aluminum, and iron are considered to be good conductors since they have many free electrons. Copper is the most common metal used as a conductor because of its relatively low cost and good conducting ability. An insulator is a material that has few, if any, electrons and resists the flow of electrons. Generally, insulators have full valence shells of 5 to 8 electrons. The electrons are held tightly. The shell is mostly full, and a very high voltage is needed to cause any electron flow. Some common insulators are air, glass, rubber, plastic, paper, and porcelain. A semiconductor has some characteristics of both conductors and insulators. Semiconductors have valence shells that contain 4 electrons. A pure semiconductor can act as either a conductor or an insulator depending on the temperature at which it is operated. Operated at low temperatures, it will be a fairly good insulator. Operated at high temperatures, it will be a fairly good conductor. Silicon and germanium are examples of semiconductor materials. Specially treated semiconductors are used to make diodes, transistors, and high-density integrated circuits which make possible many modern electronic devices which we all enjoy and appreciate.